dedicated to the research and academic quantum communities. As you know, this seminar takes place every Friday at noon Eastern Time and will be hosted on the Qiskit YouTube channel, so you can always go back and rewatch these. I'm your host, Zlatko Minev, and today I have the distinction and pleasure of hosting Professor Will Oliver, who will talk about quantum engineering of superconducting quantum bits. Hello, Will. How are you today?
Good morning. How are you, Zlatko?
Good. Where are you tuning in from today, Will?
Yeah, so I'm at my home in Lexington, Massachusetts, in the basement. Just moved to this house a couple months ago, but more or less settled in. Had our first snowstorm.
I was about to say, I'm very appreciative you could make it with us here today. There was, 17 inches of rain or snow or something like that. I'm down in New York and felt it myself.
Yeah.
And before we begin with your slides, allow me to give a bit of background. Dr. Professor William Oliver is jointly appointed at the Lincoln Laboratory as a fellow in the Advanced Technology Division. And he's also a professor at the MIT Physics ECS. He also serves as the Associate Director of the MIT RLE, Research Laboratory of Electronics. Professor Oliver was a graduate student and associate with Professor Yamamoto at Stanford University, where he worked on quantum optics, transport, and noise. Will is a fellow at the APS. He serves on the U.S. Committee of Superconducting Electronics, is an IEEE Superconducting ACS board member. You know, I could go on for a long time. I think I'll pause there. Will is pretty amazing all around. And I was just telling Will before this that I think his group has had a bit of a renaissance this year. And I believe we've had the most number of talks of any group here on this seminar series. So thank you, Will, for gifting us with another talk. And I think at this time, it's time to turn it over to you. Folks, you can ask questions of Will anytime during the talk. We'll try to keep this interactive. And Will, the stage is yours.
Great. Well, thank you, Zlatko, for that kind introduction and for the invitation to speak today. I really appreciate it and appreciate everybody tuning in from the various time zones. I moved down to campus maybe 2 years ago and started to grow the group there. And we've had a lot of papers coming out this year, and hopefully we'll continue to do that. But what I'd like to talk about today is, general topic, quantum engineering of superconducting qubits, but, necking down a little bit into noise spectroscopy and two-qubit gates with tunable couplers. And this is work that I would like to highlight from Young-Kyu Sung, who's a graduate student in the group, Uwe van Lupke, who was a visiting student in our group last year. And it's also a collaboration with Lorenza Viola and her group at Dartmouth, and in particular, Felix Baudouin and Lee Norris. So I'll highlight the various people as we go through, but I just want to mention that right up front. So I'm going to start pretty basic here, and then we'll get into some more technical detail in a moment. But just at a high level, if we want to build a quantum computer, and I think most of us here do, you need to have an architecture to do that, right? And this one that I'm showing on the right is due to Cody Jones. He did this while he was also in Yoshi Yamamoto's group, and he's now working with Google. But, basically you have many layers. You probably are familiar with many of these from a classical computer. At the top is the application and computer interface, if you want to think of it that way. And at the bottom is the hardware, the physical qubits. And in between are many other layers, like logical controller, compiler. Classical computers have those, of course. And then active error correction and passive error correction. And I'm going to talk mostly today about the passive error suppression. But let's go through these first three layers, and I like to think of these in the context of lacrosse. So we'll start with physical qubits, and physical qubits to me are, they're quite noisy. They're quite noisy to everybody, I guess. And it reminds me of this guy trying to play lacrosse, but doing it in the way that you should never do. And that is, if you're familiar with the sport, you carry a ball in a basket on a stick. Okay, and you don't want the ball to fall out. And of course, you have to run down the field. And so this guy is running down the field, but he's just holding the stick level. And as he runs, the noise of him running, his body bounces up and down because his environment, basically the ground, it's not perfectly flat. And his running is, jiggles him up and down, and the ball quickly falls out. So of course, that's not how you play lacrosse. There are things that you can do to prevent that from happening. And that is analogous to passive error suppression. And in particular, what you do is you cradle, you rotate your hand back and forth by about 180 degrees, and we'll see a direct analogy of that in a moment. You don't think about it, you just do it, right? It's not active feedback, it's passive. You just always do this while you're running, and this is what it looks like. And you can see that by doing this, we've decoupled the ball from the noise of the player running down the field on a bumpy ground, right? Ball stays in the basket, that's what you want. And then of course, he'll eventually score here at the end. Okay, so that's all well and good. We've eliminated a lot of the noise sources by doing this, but we haven't eliminated them all. And of course, even if you're cradling, occasionally the defense, the big D or decoherence, is going to come up behind you and basically knock the ball out. And the cradling doesn't prevent that, right? That still happens. And when that happens, what you need to do is first recognize that it happened, okay, an error occurred, identify where the ball is, so what kind of error occurred, where did it go, and then you go back and you actively pick it back up. And once you do that, you start cradling again and continue running down the field, right? And that's active error correction. So what I'd like to talk about today is passive error suppression and how we use it for noise spectroscopy. Okay, of course, we're using superconducting qubits. I think everybody here is familiar with them, but they're basically LC harmonic oscillators. We use a Josephson junction to impart some nonlinearity, and that basically gives this anharmonic potential here, but it's only slightly anharmonic. The way it's shown is just this LC circuit. But of course, this is one of a Mendeleev table full of artificial atoms or superconducting qubits by adding more capacitors or more junctions. And some of these can be highly anharmonic, meaning that the 1-2 transition is very different from the 0-1 transition in frequency. Some of them are only weakly anharmonic, like the transmon or the C-shunt flux qubit. So there's a whole slew of them, but basically the point here is that you have a lot of design parameters related to the properties of the junction or the capacitor or the number of junctions. And from them, you can design qubits that have a particular transition frequency, a degree of anharmonicity, high or low, positive or negative, and also sensitivity to noise. Now often, and you can trade those sensitivities off for one another. Now often, you will want to reduce those noises as much as possible and design around them. But sometimes if you're building a sensor, you may want to build a sensor that's particularly sensitive to a noise source that you have. So you can do that with superconducting qubits, and it's a feature. Now, the coherence that we're fighting to save, or the decoherence we're fighting against, arises due to materials and fabrication, largely. That's not the whole story, but that's a big part of it. I'm showing here at the bottom, going from a large wafer, 200 millimeter wafer, down through 5 qubits to 1 qubit, down to the loop with the 2 junctions, and then a small Josephson junction here. And so we fabricate these on silicon wafers using standard tool set that you'll find in a CMOS foundry. And of course, we have to have materials, and the materials have many potential sources of noise, whether it's charge fluctuations in the substrate, broken Cooper pairs or quasi-particles, as we call them, in the junctions tunneling across, magnetic flux noise, losing energy to the bias lines that we use to control it, et cetera. There are many different examples of noise sources that we have, and we need to identify them and characterize them if we're going to eliminate them. Now, even if we start with perfect materials, as soon as we fabricate, like I show at the bottom, these devices, we can introduce defects. And so it's not necessarily enough to start with, you might think in some way, okay, epitaxial materials, I'm going to grow it in my MBE or make it otherwise, and everything will be great. But that's not really the case, because then you fabricate them. And when you fabricate, of course, you can leave behind residues. You might introduce oxides on surfaces. You might actually have some physical damage that you introduce. And all of these can lead to these, quote, 2-level systems modeled in this way on the right, which can both take energy away from your qubit, can also give energy to your qubit, and dephase the qubit. So these are the types of things that we need to fight against, and we need to characterize them to do that. And there's been a remarkable improvement in the coherence times called T1 and T2 due to materials improvements, fabrication improvements, design improvements. from groups worldwide. I mean, this has been an ongoing effort for the past 20 years, and we've improved about 5, almost 6 orders of magnitude in that time period. So it's really been a remarkable improvement. And I just list here a few review papers here that may be useful if you would like to learn more. One feature of the group at MIT and Lincoln is we don't have really a favorite qubit. We try them all because they each have features that we find to be interesting. And so here are just some coherence times that we have in qubits that we have made. Okay. Now, if you want to improve coherence, there's basically 2 ways to do it. One is you just accept the fact that you have defects and you design your qubits to avoid them. And if you go back to, say, the early 2000s, people were making qubits with capacitors, for example, that were parallel plate. And the electric field, as you know, is almost entirely between those 2 plates. And if you have a lossy dielectric in there, then that means that dielectric is participating 100%. 100% of the electric field density is in there, and the qubit can lose energy that way. And so one of the major advances made at Yale, and here's Hani Paik's result here, was to put that qubit into a large 3D cavity. So it's still a 2D qubit, but it's in a 3D cavity, and you design not a parallel plate capacitor, but a lateral one. And by doing that, the electric fields go from one plate to the other, but most of the electric field density that you see here is in vacuum of the package, right? And only a very small percentage of it is actually passing through and interacting with the defects, right? And it looks like a contact potential almost. And so the result of this is that, of course, you can only lose energy if you're in contact with those defects. And so the T1 times went up substantially by doing that. Now, these are rather large, and so you can back off a little bit, but still use this concept in a 2D geometry to see advances. And this was done by Andrew Hauck back in 2008, also at Yale, and also by Fei Yan in our group, and in fact, Matthias Steffen earlier at IBM to make capacitively shunted flux qubits. Okay. So that's one way, and we've leveraged that quite a bit as a community. It might even be running out of steam a little bit. And so that leaves us with number 2, which is eliminate the defects, just get rid of them. And that's a hard problem because it requires what you see here, this virtuous cycle of material science, analysis, fabrication engineering. Of course, then you have to do cryogenic testing. And then importantly, what I'd like to talk about today is measuring what you've got, right? And having a way to characterize the noise and the defects in your system. So that's basically an introduction for what I would like to talk about. Now, of course, what we do then is we measure coherence times, and we infer from those coherence times, often as a function of frequency, what the noise sources are in our environment. There's 2 types of coherence times here. One is T1, which is energy decay. That's how quickly the qubit will lose its energy to its environment on average. And the other is T2, which is a combination of energy decay and dephasing. And I'll talk about this in just a moment. Okay, so let's remember what these coherence times are from a Bloch-Redfield model. Bloch-Redfield basically assumes that the correlation time is short, and that will lead to exponential decay functions. And if you look at a density matrix for a superposition state weighted by alpha and beta, you basically get this form, and you have longitudinal terms on the diagonal, which relate to the qubit's population, and then you have off-diagonal terms or transverse terms, which relate to the coherence of the qubit. So we take them one at a time. The longitudinal terms lead to a longitudinal relaxation. That's T1, or 1 over T1 is the rate gamma 1. And that's basically you prepare the qubit at its excited state. By convention, that's the south pole, if you think of this as the planet Earth, and then it relaxes back up to the north pole, and the time scale over which that happens. We're going to talk a lot about transverse relaxation, or coherence, and that's T2, or 1 over T2 is the rate gamma 2. And if you're on the equator, there's basically 2 ways that things can go wrong. One is, of course, you have a portion of your superposition state, which is in state 1, and that can just relax back to 0. So, of course, T2 has to depend in some way on longitudinal relaxation, gamma 1 or T1. But even if you stay on the equator, the other way that things can go wrong is that you could lose track of which way you're pointing, which longitude am I pointing at? And that's called dephasing, because you could think of it as a phase around the equator. And over time, the phase diffuses and you lose track of where you're going. Okay, and that's the dephasing time, T phi, or the rate 1 over T phi. Now, there's a bit of one little hiccup here, and that is oftentimes in superconducting qubits, we have 1 over F type noise. And there, the correlation time is not short. It can be quite long. But fortunately, and I won't go into why, but just to say that because the time scales of this low frequency 1 over F type noise is quite different than the high frequency noise that affects the qubit. In fact, the noise that causes T1 is at or very close to the qubit frequency. So you can separate these in a way that's convenient, which is that you get an exponential longitudinal relaxation, and then you get a dephasing decay function, which we'll call chi. Sorry, it's overloaded, but that's what we call it in the community. And this isn't exponential, and in fact, it's Gaussian. But other than that, this all sort of behaves in the intuitive way that we expect from Bloch-Redfield formalism.
And Will, quick question from the audience here, and I'm sure you'll get into this maybe on this slide. What can we clarify quantitatively, like what short coherence of the noise means?
Oh, yeah. So in fact, I will get to it on the next slide, but it's the correlation time between a two-time correlator, say, of whatever type of noise we're talking about. Let's say it's magnetic field, and so, or the fluctuation in the magnetic field. And you could call that lambda. Lambda can represent any noise. And you look at it at two different times, at say time 0, and then at some time later tau, and that's the autocorrelation function. And if that autocorrelation function, in fact, is very narrow, or ideally even a delta function, meaning that it's 0 unless you're correlating at the same time, right? We know that intuitively that delta function in time would Fourier transform to basically a uniform distribution in frequency, right? And so, in fact, the power spectral density itself is the Fourier transform of the two-time correlation function shown here. So these are Fourier transform pairs. And so short in time means broad in frequency. Okay, and so white noise in frequency would be, in fact, corresponding to a delta correlated noise process. So we often talk about the noise power spectral density as a characterization in frequency space, as a characterization of what's happening temporally in time of our noise process. And the power spectral density is a second order power spectrum. And I emphasize that because we use it all the time, but it's useful to remember that it doesn't describe noise of all correlations. It is a second order statistic. And I mention it because we'll talk about a third order statistic later on. But for Gaussian distributed noise in particular, we know that all orders can be captured at second order. So it is a useful metric for sure for practical purposes, but it's not the whole story. Now it gets interesting here because everything I've said so far is a classical story. Classical noise, classical spectral density, but of course, quantum mechanically, these noise sources need not be classical. They can be quantum, and they may be operators, and these operators generally don't commute at different times, and that has impact for the type of noise that we have. And let me illustrate a few examples, both classical and quantum here. So we plot this noise spectral density as a function of frequency, and at negative frequencies, we say that the qubit is absorbing energy from its environment, and at positive frequencies, we say that the qubit is emitting energy to its environment. Now, classically, there's no distinction between these two. In fact, you've certainly heard of thermal noise or Johnson noise of a resistor, which is proportional to Boltzmann's constant times temperature. Here it's a capital theta. And it's basically, this Bloch-Redfield type noise. It's white noise, and it goes out to generally very high frequencies. But there will be a cutoff at some point in a resistor. Okay, it doesn't go on forever, and it's related to the temperature and the frequency that you're looking at. But generally, you can think of this as white noise. But quantum mechanically, in fact, there is a distinction between emission to the environment and absorption from the environment. And this is together called Johnson-Nyquist noise, because Nyquist was the one who first showed that this quantum side exists. And the way to think of it is that even if you're at zero temperature, okay, your environment is at zero temperature, it can give the qubit no energy, right? But if the qubit's in its excited state, it can always emit energy to the environment, right? So immediately there, we see that there's this asymmetry between spontaneous emission to the environment and absorption of energy from the environment. And that falls out naturally from treating this autocorrelation function in terms of operators, quantum operators. Now, this Nyquist noise, in fact, this dashed line is called Nyquist noise or quantum noise, is proportional to h bar omega in a one-dimensional system. And so at higher frequencies, you have a higher likelihood, or at least you have more opportunities to emit to that environment. Of course, it depends a lot on the matrix element of your qubit as well. Okay. Now, classically, we have 1 over f flux noise, for example. This is just classical noise, and classical noise is symmetric about zero frequency. And it tends to fall off as 1 over f. Here, I'm drawing it as 1 over f on linear scale, although we'll often see it as a straight line on a log scale. So these are just a few examples of the noise that impact us. Now, the 1 over f noise generally is responsible for dephasing. Dephasing happens due to noise at any frequency. And that can be contrasted with this T1 type or relaxation absorption noise, which happens at the qubit frequency. Now, you can see that this 1 over f flux noise does cross the qubit frequency at some point, and there it can, of course, contribute also to relaxation and absorption. But generally, it's highest at low frequencies where it's just causing dephasing.
And Will, this is very interesting. We have a question from the audience about the quantum Nyquist noise, the h bar omega, and what is the relationship between that, the 0-point fluctuations, and potentially 1/2. I don't know if there's more of a comment to make there.
No, I think that, the question is, what is that noise, right? And because it's not a physical noise in the sense that something's jiggling in the environment. Remember, in this intuitive picture, I said the environment's completely cold. It's not jiggling at all. It's a catcher waiting for the pitcher to throw a baseball to you, right? But you can ask the question of what is the sort of equivalent noise that one would have to induce that transition, right? And through that classical thinking, you can come up with a level of noise, which here is proportional to h bar omega. And in fact, I think as you alluded to, it's the 0-point fluctuations. So therein, you can make this connection to quantum. But think of it intuitively as an equivalence of how much noise would I need to induce that transition.
Mm-hmm. Yeah,
okay.
Good, thank you.
Yep. So with that as an introduction, let me get into some of the topic of noise spectroscopy. Okay, so noise spectroscopy is meant, of course, to characterize the noise we have in our environment, and there's a lot of different noise. Now, traditionally, I guess, or what's maybe easier to deal with is to make some assumptions about your noise source, like say it's Gaussian, it's spatially uncorrelated, use a two-level approximation for the sensor that you're using to measure the noise. And these are all very good approximations, actually, but they're fairly specific. And more generally, you can have an environment that features correlations beyond the second order, so non-Gaussian noise. You might go beyond a two-level approximation for your sensor. Importantly, there may be spatial correlations, like a qubit's here and a qubit's there, and they somehow see correlated noise, and that has impact for error correction. And so I think that, we were looking at this. We did a lot of work early on the specific side, but recently we've been focused more on the general side, and I'd like to just share a few of those results. But before I do, I'll talk about the specific side just to get our bearings straight. So when we talk about dephasing, we're talking about basically energy levels of our qubit that jiggle. And before they jiggle, let's imagine the ideal case, which is that you have a superposition state weighted by alpha and beta. Of course, state one is at a higher energy, let's say, so it accrues a phase at a rate that's related to this energy level separation, 0, 1. And at this point, in the absence of noise, these are just fixed numbers, right? There's no stochasticity here, right? And so at any point in the future, you can predict and tell me exactly what this phase is. But of course, we live in an environment that has noise, and so the qubit energy levels will fluctuate. For example, due to 1/f flux noise threading through a loop, a squid loop in your qubit. So that jiggles the energy level separation, and you can think of it as having an average energy or an average phase as a function of time, plus this stochastic portion. And it's the stochastic portion that, in an ensemble average sense, will give you dephasing. Now, we saw that this off-diagonal term in the density matrix is where this phase lives, this dephasing occurs, and it occurs in an exponent. And you can calculate the impact by ensemble averaging, that's the brackets, of the time integration of this energy or this phase. The energy normalized by this decay rate times delta t then gives you the phase. Okay, so you integrate that. And for Gaussian distributed fluctuations, which often occur, the leading term in second, so you get a square here in time. And this makes sense, is that as time increases, obviously there's going to be more decay, but how much decay you get is going to be related to how much these energy levels are changing for a given fluctuation in your environment, where lambda is indicating, say, the flux noise that you have. All right, and that comes in squared as well. And then the question is, well, how much is that fluctuating? This d lambda tells me how much my energy levels will change for a fluctuation in lambda, and then how much lambda do I have? And the amount you have there is basically the strength or the variance, which you calculate by integrating the power spectral density that we looked at. And then there's this factor g here, and that basically depends on what we do as experimentalists, and we call it a filter function. And it basically shapes the noise. And then that's what I'd like to talk about now. So what we're looking at here is a Ramsey experiment. And with Ramsey, you have 2 π/2 pulses, which bring the block vector down to the equator. And then what I'm simulating here is, in the presence of noise, we can see that sometimes the energy levels got further apart or closer together. And in a rotating frame, that means sometimes the block vectors are going to go they're going to rotate in a clockwise or counterclockwise direction. Now, basically, this is 1/f flux noise. I'll just say that by fiat. You can see the spectrum here goes as 1/f, and now I'm on a log scale, so it's straight. And basically, a lot of the weight is at low frequencies. So we might even say that during this relatively short experiment of duration tau, the noise doesn't change. That's a quasi-static approximation, but it's a good one. And if we make that assumption, then the energy levels are basically fixed for one experiment, and then they change to another value due to the noise for another experiment, and then to another value for another experiment, and then you do thousands and thousands of experiments in ensemble average. Okay. So if you do that, then basically your energy levels are fixed as a function of time, at least for this gray region, and that's a boxcar. And the Fourier transform of a boxcar is a sinc function. And the sinc function is shown here in blue, and it's weighted very heavily at 0 frequency. And so it's a window, a filter, that lets in noise at low frequency, which is exactly where 1/f flux noise is noisiest. So this is a terrible idea. This is what you don't want to do. And it's the reason why things become so depolarized in this example. So in fact, what we do is we'll apply a pi pulse right in the middle. This is called spin echo. And as you know, that basically inverts the system and refocuses these together, and this looks much less depolarized at the end. And the intuition here is that you now have 2 free evolution regions, but now of duration τ/2, and one comes in fact, with a minus sign due to this pi pulse when things are inverted. And the Fourier transform of that gives a filter function in green, which has a peak at a higher frequency. In fact, it's 0 at 0 frequency. And therefore, less noise comes through this filter or through this window. And so this is how the pulses we do in time shape the noise that the qubit sees in frequency from the environment. The environment's always got this 1/f flux noise, but the qubit's sensitivity to it changes depending on the pulses that we apply.
And quick question from the audience, maybe we'll also get to this soon, that could we distinguish, or to what degree can we distinguish the gate errors from the environmental noise?
Oh, you mean like a systematic error, I guess. Yeah, so
either systematic or fluctuations in the amplitude and phase of the gates and things like that.
Yeah, so we can design the way that the qubit couples to noise, right? To some degree, that's some of the flexibility of having these artificial atoms. And so, for example, I could design a qubit that's highly sensitive to flux noise, or highly sensitive to charge noise, or even highly sensitive to fluctuations in the amplitude when I'm driving it with a, say, a Rabi oscillation driving it. And so we can distinguish to some degree the noise depending on how it couples into our qubits and the type of experiment we do. Now, those noises tend to be stochastic, right? And so we can correct them in this sort of way, dynamically decoupling them. There are also noises that are systematic. So for example, I think I'm doing a pi rotation, but in fact I'm over-rotating. But I always over-rotate in the same way because I didn't calibrate my electronics quite properly, let's say. That, of course, you can also measure and fix through either calibrating better, or there are pulse sequences that have been developed over the years, mostly in NMR to begin with, where you can do composite pulses. You pulse, you do effectively a pi rotation, but you do it with more than just one pulse. You use a few different pulses. And by doing that, you can mitigate or basically become insensitive or less sensitive to the over-rotation errors that you have. So those are basically a palette of different approaches that we have to deal with these types of systematic and stochastic noises.
Yeah, so I guess that's like the XY, 8, 16, 32, and so on for over-rotations and then fluctuations on the actual amplitudes of the gates that aren't systematics. I guess those we probably think aren't just, well, even though you're playing hundreds and hundreds of gates, then I guess we think that's anyway a very small effect on all of this.
Yeah, well, in fact, what you can do, I'm going to show in a moment that you can go into a rotating frame. And in fact, there's some benefits to doing this type of noise spectroscopy in a rotating frame. But when you go there, now you, of course, rotating frame, you're driving ideally at a fixed Rabi frequency, but those fluctuations fluctuate the Rabi frequency. And a lot of these noise spectroscopy protocols that we use during free evolution, you can apply during driven evolution. And in fact, there's analogs there. Something called a rotary echo is the driven evolution analog to the free evolution spin echo. And so a lot of the noise sources that you would find due to a drive have a direct analog in the rotating frame that as do these types of noise sources in the free evolution frame.
Yes. Thank you very much, Will.
Yep. So of course you can keep increasing the number of pi pulses, and then this will keep pushing down the dephasing, and eventually you're left with just the T1 component. Don't forget, if you're on the equator, of course, you can just relax back to the ground state. That's kind of a limit on your T2, and it's twice T1. But you can mitigate the dephasing component, and you do it by basically increasing the number of pulses and shifting this filter to higher and higher frequencies. And as long as your noise is decreasing with frequency, that's a good thing. It would be a bad thing if your noise was increasing with frequency. But what you recognize is that you can invert this problem and then say, well, maybe I can tune the shape of this filter, make it narrower, and you can do that by changing either the time, or in fact, you can change it by the number of pulses, and basically move it around to sample the noise spectral density that your environment has. And so we've done a lot of work in that area. Some of those are listed, those publications are here, and there have been many groups worldwide doing it, where you can map out anything from the millihertz even out to the gigahertz regime by using this concept or related concepts. Okay, so that's noise spectroscopy using dynamical decoupling. And so I won't read through this whole thing, but the point is that we've mapped out in this 2013 paper free evolution versus driven evolution for both T1, longitudinal relaxation, or T2, transverse relaxation. Here's that rotary echo that I just spoke of. There's a nice analog in here for driven evolution. But again, all of this was presuming sort of nice Gaussian noise. Okay. So the question is, what happens when you don't have that? Okay, and so we've been thinking about that lately. And where you'll see it is in, for example, in qubits that are tunable, say, with flux, and they have say a curvature here. Now this is a flux qubit, but you also have something like this with a transmon qubit just pointed down. But this is a flux qubit, and your transition frequency goes as this hyperbola. where delta squared is, you know, an epsilon squared or parameters. Here, the flux modulates epsilon. So let's bias this at a point far from the what we would call a degeneracy point, and you know, where this frequency is approximately equal to epsilon. Epsilon much larger than, say, delta. Okay. And you have some Gaussian noise in your environment. We know from, say, the central limit theorem that if you have lots and lots of fluctuators, that whatever their intrinsic statistics are, if you get a lot of them, it'll become Gaussian in the large N limit. And so if you have that fluctuation and you have a linear response of your qubit to that fluctuation in frequency, then that's just Gaussian dephasing. And that's characterized very well by the power spectral density that we just talked about, this 2-time correlator. And I'll take the opportunity here to say that there are 2 times, but if there's a time invariance in your noise, then we can set one of those to 0, and then we have just one time, which is basically delta t, and therefore we have just one frequency. Okay. Now, if you're biased at this point here, the sweet spot or degeneracy point in flux qubit language, you know, to second order in epsilon, you're going to oscillate about this point in this way. And it looks like a quadratic, you know, Gaussian noise. So you're taking your Gaussian noise and you're squaring it. Okay, squared Gaussian noise is no longer Gaussian. Okay, so this really happens. And in fact, it leads to higher order spectra, where now your correlation function isn't just a 2-time correlator, but a 3-time and a 4-time and an n-time, and these are called higher order spectra. And again, if there's a time invariance, you may have say an nth order correlation function, but you have n-1 frequencies because you set one of them to 0. Okay. And we're going to look at the 3rd order correlation function, which has 2 frequencies in the spectral domain. Okay, but basically what's happening here is you took Gaussian noise, which was blue, right, that we saw up here, you know, basically symmetrically distributed about some value, say omega 0.1. But when you square it, you just notice that I can only go to higher frequencies, even though about this mean value, my noise can fluctuate plus and minus. Okay, and so now you can see this is highly non-Gaussian. Okay, so this happens. So you can verify the non-Gaussianity of the noise by doing an experiment like this. This is CPMG. There are 2 pi pulses. We just saw an example of it. Okay, you do your first pi over 2 pulse, you do a second pi over 2 pulse, and then you read out. And we look at how much phase accumulates, and then we also look at the decay rate here. Now, the phase accumulation for Gaussian noise, in this case, ideally is 0 if we refocus perfectly. But in a non-Gaussian case, as we're going to see, that's not true anymore. And it goes as the cube root of the power, or the cubic of the power. And so what we've done here is we've injected noise purposefully, and as a function of that noise, measured the phase accumulation. And you can see that, that it increases linearly, at least on this log scale, according to the 3rd order in power, which we expect. Now, you see that it starts to deviate at higher powers, and that's because we're not just sensitive to the 3rd, we're actually sensitive to the 4th, 5th, 6th, et cetera, in principle. But in this region here, it is following the 3rd cumulus. Now, there's also a decay rate, the phase decay rate, which for Gaussian noise, of course, it does decay, and it decays proportional to power. But for this non-Gaussian noise, it goes leading order power squared. And we can show that that's true here. So we have it following as a function of the noise power. Again, the phase decay rate going as power squared. So this is just to show that we can measure this effect. Now, it's interesting how it impacts us. And so let's look at this first case where we have Gaussian dephasing noise in our environment, and we're biased at a place where the transfer function is linear. Okay, and we're now going to do this CPMG. So we have 1 pi pulse. Okay, it refocuses, keeps going. We have a 2nd pi pulse, and you can see that on this block sphere here, we're looking at a side view, and here's from the top down, that basically we refocused, and so the net phase accrual is 0, right? And that's kind of our intuitive picture, I think. But we're now going to look at non-Gaussian noise at this quadratic point, and we're going to see that that's not what happens. Okay, so we have the first pi pulse, and it looks like we rephase. Okay, but we get the second pi pulse, and we realize Oh, what's happening? Oh, yeah, so we got extra phase. We got another 10 degrees than we expected, even though we positioned these pi pulses exactly where they should go for Gaussian noise. And so this is a consequence of having this higher order correlations in the noise in your environment, and its impact on experiments like these refocusing experiments. So it's real, it matters. Now, I won't go into too much detail here, but just to say that just in the way that we were able to develop one-dimensional filter functions to look at the noise spectral density as a function of frequency, we can develop two-dimensional filter functions to look at higher order spectra. In this case, the polyspectra has two frequency components. Okay, so it's called the bispectrum, and it corresponds to a third order correlation function. Okay. Now, the way that we do this, again, is we, in time domain, generate pulses in a specific way. And by generating these pulses, we can map out filters in the frequency domain. And what I want to mention here is only that there's certain symmetries for this bispectrum where you basically only need to look at a small portion, about an eighth of the spectrum or spectral content in 2 dimensions to, and then through transformations, you can basically map out the rest of this. Okay. So again, pulses in time correspond to filter functions in frequency, but here they're 2-dimensional filter functions.
And just to clarify, Will, the omega-1 and omega-2 here, that's still the frequency of the noise.
Yes, that's right. It's the frequency that of the noise that arises from these third order correlation functions in time. That's right.
Great. Mm-hmm.
So as we look at it, here's the bispectrum reconstructed in an experiment. And you can see the top-down view here and the side view here. And then here's what it looked like ideally. So this is noise that we generated, so we have full control over it. We applied it to the qubit, pretended that the qubit had no idea what's going on, and then used the filter functions to reconstruct that noise. And so this was the first time that we've been able to reconstruct noise higher than second order.
And what's the cost in terms of sequences? It seems like here you need quite a variety of sequences. Is that right? Or do you need to run like hundreds, thousands, tens of thousands?
So the number of sequences is not unrealistically high. In fact, you can see here that the sequence number, there's 11 sequences here. So it wasn't ridiculous. Now, of course, you may need to sample, you may want to sample more densely. You may, I think then it becomes a question of, what your noise spectrum actually looks like in detail. So it gets, just as, how many pi pulses do I need? And how many frequencies do I need to look at to sample the 1/f noise, right? And if you believe it's 1/f, you probably don't need that many. But if you have no idea and you're looking for some, TLSs here and there, then you might need to sample more densely, and that requires more sequences and more filters.
And I guess while I have you on pause here, maybe you'll get into this, but a lot of the assumption here is predicated on the time invariance of the noise. And one of the favorite questions by theorists and also a question in the audience here was, well, what about non-Markovian noise? Because there have been many papers, and I think you've also reported on non-Markovian noise for superconducting qubits for time non-stationarity of that. Could we map that? Is there a tomographic process, or is there some characterization for non-Markovian / how does that potentially create bias or affect these results?
Yeah, so that's a great question, and it's an important one, as you said, because I think error correcting codes in particular, need to know what type of noise you're looking at, right? And so I'm going to get to just in a moment to spatiotemporally correlated noise, but to quickly answer the question, these techniques do, over the length of the experiment that it takes us to look at this, do require that the noise has some invariance to it. And of course, if the noise is changing in the background while we're measuring it, that's clearly going to impact the ensemble averaging that we do, because we need to sample it many, many times. And if it's changing, then that's not captured here, or it's going to wash out what we see here.
Yeah, and I guess most of the fluctuations that people tend to report tend to be on the scale of hours or maybe even minutes, or maybe, there's this quasi-particle creation event or something like that happens that changes the system more stochastically.
Yeah, that's right. And, it gets to the question of, what really is time invariance, right? And, theoretically, you think about infinite time, right? But of course, our experiments only last so long. And so then, the notion of bandwidth comes in. And what matters is it really changing during the time that I'm looking at it, right?
Mm.
And does it change on timescales longer than that? And if so, what is that timescale?
Yeah, I guess another way maybe to rephrase it is, if you rerun this experiment, a day later, how different would that be? I suppose most times would be pretty similar, but maybe every few days there would be kind of a dramatic change. But maybe that's, we don't need to go there if you don't want to.
No, it's okay. It's a great question. And we have Greg Calucine at Lincoln, and Kyle and others are looking at, particularly in the context of T1 fluctuations, what are the statistics of those T1 fluctuations? And we know that they fluctuate slowly over time, right? And let's say you looked at a really long time, does that then again look invariant, or is it truly non-Markovian? I think these are very interesting questions.
Yeah, thank you. And I guess the other question that maybe you'll get into later that I would be curious if you'll make some comments on is, so far we have individual systems without neighbors, but it will be interesting to see, how neighboring quantum systems also affect all of this. So I'll just
Hold tight. I'm going to get there. All right. I'd just like to point out this analogy between free and driven evolution, because I think it's really, it's really beautiful the way physics works in general, but then in here as well, that, if we look at the sort of free evolution, the qubit as we have it, and we look at inversion recovery, sorry, I got my arrow pointing the opposite way, north pole to south pole as energy decay. That's the way we usually think of it. But if you do what's called spin locking, which is you drive your qubit at a particular frequency, Rabi frequency, this is called spin locking. And now your qubit's quantization axis is along your driving axis. Let's say it's along X. And so relaxation along X is called T1 rho. You're in the rotating frame. And now you can think of this as a qubit whose quantization axis is X, and the frequency separation is the Rabi frequency, how strongly you're driving it, okay? So that's T1 rho. And then you can also make an analogy to what's happening on the equator, Ramsey experiment, spin echo, CPMG, et cetera, the T2, right, which would be on the equator in free evolution. But now that you've rotated this 90 degrees in your rotating frame, that becomes, for this picture, the YZ axis. And so some of these experiments then are, in fact, Rabi, or as I mentioned, rotary echo that you can do during driven evolution. And then, so this is called T2 rho, which is in the rotating frame, or you can call that T Rabi. Those are the same. So there's this very nice analogy, and it turns out that the noise spectroscopy we do now is mostly in this rotating frame because it allows us to go over a wider frequency range, and actually it gives us better accuracy. But all of the things that we talked about intuitively in free evolution will translate to this driven evolution frame. Okay. So what I'd like to talk about now is going beyond a two-level system model. So the spin locking is usually noise spectroscopy is done with two levels. And as I just mentioned, we'll often do it in this rotating frame or spin locking frame. So we're driving the atom, and what that does is it creates a pair of dress states. Again, you can think of it as a qubit along the x-axis. And the level splitting here is the Rabi frequency, which you tune by the amplitude of your drive. Okay. And now we look at relaxation in this dress state basis, and we can relate it back to the noise spectral density of the qubit by itself. Okay. Now, one feature here is that because the frequencies now are not necessarily large compared with temperature, we just have to keep in the back of our mind that when we're measuring relaxation, for qubits that are 5 gigahertz at 10 millikelvin, maybe that relaxation almost predominantly is spontaneous emission to the environment. The environment is so cold, it almost never excites us. So 0 temperature limit. But here, we could set that Rabi frequency to say 100 megahertz, which now is colder, yeah, right, than the physical temperature. So the environment's hot compared to your qubit, and so we actually have to keep track of that temperature and the polarization that results, or depolarization that results. Okay. But of course, we know we work with multi-level artificial atoms, and you have different transitions, not just 0, 1, but you also have 1, 2, and 2, 3, et cetera. And so in this work, we're looking at driving this second transition as well, which gives us another pair of levels, another spin locking frame that we can work with. And generally, this extends out to any j minus 1 to jth transition that we may have. Okay, so it gives us multiple sensors. And one thing to note is that if you have a qubit which is, say, like a transmon or a C-shunt flux qubit, where the anharmonicity is small, the difference between the 0, 1 the 0, 1 frequency and the 1, 2 frequency is not very large compared to the frequency itself. So maybe a few hundred megahertz on 5 gigahertz. And the consequence of that is that when you drive these, you start to see impact. So you're driving what you think is a 0, 1 transition, but you're also off-resonantly driving the 1, 2 transition. And that these dress states start to push against each other, right? You get level repulsion due to these dress states. And that impacts the frequency that you're actually measuring noise at. So for this reason, using a transmon, for example, this spin locking frequency type noise spectroscopy only works up to about 100 megahertz. As soon as you get up to the anharmonicity level, you start to get errors. Okay, so that's one reason that we wanted to do this. The second is that you can actually use multiple sensors to distinguish multiple noise sources. So, and I'll show an example of this in just a moment. Okay, so this is the device. We have 3 qubits, but we're only using the rightmost device as our noise sensor. It's a transmon. It's split into a squid, so it's sensitive to magnetic field, or it's sensitive to magnetic field, so that's flux noise, but it's also sensitive to photon shot noise in the resonator. And then these other qubits, we're just putting far off resonance, so we don't need to think about them, just gray them out. So what we do is we generate engineered flux noise and apply it to the qubit. And we also generate photon shot noise and apply that to the resonator. And so we have these 2 different noise sources impacting our qubit. And what we want to do then is use the qubit to measure those both by using these 2 different transitions. Okay, so we bias our transmon at a flux sensitive point. That means that it's not at the sweet spot, but off the sweet spot, the operating point. And the relaxation times here for whether we're a 0, 1 transition or a 1, 2 are between 30 and 60 microseconds. That's the T1 time. So the energy level fluctuations due to flux noise come in through the Josephson energy, right? Through the flux here, the critical current, or EJ. And so the 0, 1 transition we know is given by the square root of 8 EJ Josephson energy times charging energy minus the charging energy. But the point is that if EJ is much larger than EC, the anharmonicity is basically constant under flux noise, which means that the difference between the 0, 1 and the 1, 2 transition frequency is basically just this EC. That's it, right? And that doesn't depend on the flux that we're applying or the flux noise that's being imparted. So if we look at the fluctuations in these frequencies as a function of, say, flux noise, it's basically taking the derivative of EC with respect to flux, which is 0, right? And so intuitively, if we want to look at that, basically what's happening is we're getting fluctuation and the energies are changing, but they're changing in exactly the same way, whether it's 0, 1 or 1, 2. So for flux noise, the spectral densities that we would extract from these 2 cases is identical. Now, that's not the case for photon shot noise, as we know. We know that with photon shot noise, there's a level-dependent dispersive shift. So here, sorry for the overloading of chi, but the dispersive shift for 0, 1 transition is different than for 1, 2, okay? And the change in frequency comes in as twice chi times the number of photons, its fluctuation, okay? So for photon shot noise, which comes in, the power spectral density has a quadratic scaling with chi, but the chi's are now different for these two levels or transitions. And so with flux noise, if we just look at flux noise and extract our power spectrum using these two different approaches, one using the 0-1 transition and one using the 1-2 transition, we find that the data are exactly the same, right? And we expect that because the response of the system is the same for these two types of noise. But for photon shot noise, it's different, and it's different by about a factor 1.6. And so this allows us to extract, basically, or at least identify what is photon shot noise portion and what is flux noise portion. Okay. And so the experiment that we do to distinguish this is we apply them both simultaneously. We look at boxcar-shaped flux noise over this frequency range, and then we add to it photon shot noise through the resonator, which is why it has this Lorentzian spectrum. Okay, and when we make the measurements, we can see a few things from the two sensors. So one is that up here, where we're in the tail of the Lorentzian from the photon shot noise, basically we're just sensitive to flux noise, and whether we're looking at the first transition or the second transition, we get the same result. We also notice that we don't measure anything if we go higher in frequency where there is no engineered flux noise. And then in this region, where we have a lot of photon shot noise, or at least sensitivity to that shot noise, we see that the two sensors give us a different result, and those two results sit on top of the flux noise background. Okay, and so from this, we can extract the flux noise and the photon shot noise contributions by measuring the spectral density via these two different sensors at two different transitions. So basically what this does is it gives us, by using two sensors, it gives us a means to measure two different kinds of noise. And in fact, you could go to 3 or more sensors, and we're looking at doing that to look at charge noise. But the other thing it allows you to do is correct for this level repulsion that I was talking about before in weakly anharmonic qubits like the transmon. By using two sensors, what you can do is measure and account for this level repulsion so that you can now go up to higher frequencies in your noise spectroscopy. So that's another benefit of this. Okay. And this is work, I should say, by Young-Q, and you can find it in the archive. It's currently under review. So I realize I've been talking a little bit too slowly here. Let me just highlight a couple of results here on spatially correlated noise, and of course temporally correlated as well. What we find here, the correlation is spatial. The temporal noise is not correlated here. What we do is we have two qubits, a red one and a blue one. These are then coupled to a common feed line, which is basically a resonator. So they have a common resonator. And what we want to do then is put in some photon shot noise into this resonator, which couples to both blue and red qubit. And so we expect noise correlations to occur. And let me just quickly say that what we're measuring here is basically a joint correlation function between the two. It's the Z, okay, Z1, Z2 correlation function. And what we find here is that, what's the experiment we're doing that I'm showing you is that we're detuning the cavity noise drive shown here. It's detuned by about 2 megahertz off of the cavity. We're dressing qubit 2 at a fixed frequency, and then we're sweeping qubit 1 with respect to that. Okay. And what we find is when everybody's lined up is that you have some strong correlations, as you would expect. And what's kind of interesting here is that these correlations, because qubits blue and red are connected to each other, in fact, this correlation lives on even at long times. So there's a negative correlation that arises due to a residual 2-qubit swap interaction in the presence of this noise. Okay, but this is just to show that there is correlated noise. This is a correlation function between 2 qubits. There's an impact that's correlated. Okay, and it matches simulation of a master equation. And this was done in collaboration with Lorenzo Viola's group at Dartmouth.
And to account for that, was that sort of a ZZ type of coupling to account for that correlation, or was there something else? Basically, I guess you have a model which captures all of this effect, and so I guess then you have a sense of what the reason for this correlation is between the two qubits.
Oh, it's just that the correlation exists because they're both coupled to this photon shot noise, and then therefore they're if there's photon number fluctuations in here, they're going to impact both the blue and the red qubit.
And does the direct coupling between the two qubits play a role in here as well?
Yeah, in fact, it does. And so it's this residual swap interaction that's the reason that this continues on with a negative correlation. In fact,
good.
Yeah. That may not be obvious, but it does bear out in the simulations.
Yeah, exactly. Okay, thank you.
Yep. So basically, at this point, what we've done is shown that we can tomographically measure this by the following protocol, which is that we basically initialize our qubit with some input states between them. We apply some noise, or we look at their evolution under the impact of noise, and then we make measurements. And then we look at this in different bases. And we then compare that to master equation simulations, and through basically a reconstruction protocol, make an estimate for the power spectral density. And I would refer you to the paper for more details. Basically, it's kind of a brute force method to do this. And I think what we would like to do next is abstract that down into some rules that apply, not generally, this applies generally, but break that down into some rules that you can apply to different types of noise given the type that you have. And just to show the result that we were able to reconstruct the noise spectral density for qubit 1 and for qubit 2, but we could also reconstruct the cross spectral density, which is the representing the spatial correlation between these two. And so let me refer you to this. It was recently published in PRX Quantum. A lot of detail in that paper about how it works. And so we'd like to abstract it, but also improve the accuracy. You can see here that there's a bit of a difference between what we measured and what we saw, and we're still working through why that is. And now I really am out of time, so let me just basically flash the result and then show the paper. So we've been working with a tunable coupler where you have two qubits mediated by a tunable coupler, which is just a qubit. But the feature here is that the nearest neighbor interactions between the coupler and the qubit can come in with a different sign than the next nearest neighbor interaction. And what that allows you to do is by tuning the coupler, you can couple the qubits with either a negative or a positive coupling strength G, and you can in fact turn it off. That's basically the feature here. And I'm just going to flash through some slides here where you look at different bias points, and you're going to look at the oscillation of these swap operations, and you're going to see that in fact we can tune the frequency of the swap operation and in fact turn it off. Right now the qubits aren't coupled effectively, and then turn it on again with the opposite sign. So this all works. And this is work by Young Q again, where he made a 2-qubit device coupled by this tunable coupler, and it's basically a realization of this. And what I'm going to say is he demonstrated, and I apologize, I have to go fast here, but look at the this archive paper for more details. He was able to demonstrate both a CZ gate using this tunable coupler, and he was also able to demonstrate an iSWAP gate with the tunable coupler. Some features is he suppressed leakage in the CZ by using optimal control pulses, and by doing that was able to get about a 70% improvement in the error rate. So with just turning the coupler on and off using effectively a boxcar, we got about 99.25% fidelity. But by using an optimal pulse sequence, a Slepian pulse sequence is one pulse, right? He was able to get up to 99.76%. So this is quite good, and it's almost, the point here is it's almost basically it's T1 limited. So that's great news. On the swap side, he was able to basically suppress parasitic ZZ interaction by using higher levels of the coupler. And I won't be able to go into detail because I don't have time here. But basically, the higher level of the coupler is pushing down and back against the level, the ZZ parasitic ZZ interaction that we get sort of intrinsically in these qubits. And so by taking advantage of that and tuning the coupler in a proper way, you can basically null out any phase shifts that happen from the ZZ interaction. So again, I'd encourage you to look at the paper, but with this, he was able to get almost 3 nines, 99.87% iSWAP fidelity. Let me emphasize, this is just the 2-qubit interaction portion. There are also single qubit rotations that would need to be done on top of this. But if you look at the phase accrued due to ZZ interaction, you can see that he was able to effectively null it out over 100 iSWAP gates. So I apologize, that was very fast. Let me acknowledge my many teammates. The work was done primarily by Young Q and Uwe in collaboration with Felix, Lee, and Lorenza out at Dartmouth. But of course, it leverages our entire team at the MIT campus in the Engineering Quantum Systems group, and also the team at Lincoln Laboratory. And this is basically one team spanning 2 locations. We're all MIT, and we all are really happy to work together on this. So thank you for your attention.
Thank you very much, Will. This was really great, and thank you also for covering the latter part. Let me see if folks, if you have any more questions in addition to all the good ones we had during the talk, please post them in the comment chat box, located there or there. Oh, actually, we do have one question off the bat right here. This is an interesting one. Great work. Is Dr. Oliver looking for new PhD students?
Let me take the opportunity to say that we are absolutely, we're looking for new PhD students, and we're also looking for postdocs. As you know, the U.S. just, of course, it passed the NQI, the National Quantum Initiative, 2 years ago now, or a year and a half ago, and then the Department of Energy has announced their centers, and Lincoln Lab and MIT campus are participating in 2 centers, one at Brookhaven and one at Berkeley National Lab. And so as a result, I'm expecting that the size of the campus group will probably increase by 50 to 75%. So we're absolutely looking for highly motivated people who are really interested in quantum information and want to make a difference. So contact me.
All right, and I think we have that probably in the chat, or Will is on Twitter. Thank you for that question. Another question from the audience: what kind of sequences, RBC, randomized benchmarking sequences, are using to measure these gate fidelities that were quoted, I think, in the last part of the talk?
Oh yeah, so in fact, they're we aren't yet using dynamical error suppression as much as one could. I think Young Q was focusing on basically looking at the coupler and then optimizing how you shift the coupler into its on and off position, and how to do that in a way that doesn't cause leakage to higher levels, either in the coupler or in the qubits, or balances out the VZ interaction that we have by taking the upper level of the coupler and pushing it down and then back up in a way that the unwanted phase accrual due to ZZ interaction is nulled out. But I think you're right that there certainly is opportunity with the single qubit gates to do dynamical error suppression, or also refocusing in this 2-qubit subspace.
Yeah, and just as a general question comment, having worked with both the fixed coupling and now also having this coupler in between, how much more difficult and how much of an advantage does that give you? Is it in a sense worth the extra complexity, or is that too early to say?
I think it's worth it, to be honest. I think there is more complexity. I'm not sure if I mentioned it. Maybe it was clear that we have a fixed frequency qubit, we have a tunable qubit, and then we have a tunable coupler. You could imagine doing this in different ways, like just having fixed frequency qubits with tunable couplers, all combinations that they're in. But what's nice about having the tunable coupler is you can turn off the coupling, right? And you can turn it off in a way that accounts for the parasitic nearest neighbor coupling. That's the real advantage. And that's not the only way to do that, but it is one way to do it. And the advantage is that when calibrating a larger system, say 9 or 16 or 25 or more qubits, it's very handy to be able to look at this piecewise, right? As opposed to having too many neighbors chattering while you're trying to calibrate or talk to just one person in the room, right? And I know that when Google did their experiment, the quantum advantage experiment in 2019, they cited Fei-Yan's paper from our group where we proposed doing this, two-qubit coupler gate approach. And I think they used it, in fact, and it helped them do the calibration. That's my understanding, is that it was easier to calibrate Sycamore than it was to calibrate the previous generation of processor, primarily because of this crosstalk issue.
Yeah, and to the crosstalk, I think I remember, maybe I don't know about the latest Google papers, but the earlier ones, there was a lot of time that went into calibrating the flex crosstalk, and that becomes quite challenging at the larger numbers of qubits, because everything, correct me if I'm wrong, but everything somewhat tends to talk to everything, and now you have a nonlinear system to calibrate because the coupler is nonlinear, so you don't just have a linear calibration, perhaps. Maybe you can comment on that.
Well, that's a great question. So we're just getting into this now in multi-qubit systems. We have a 3x3 qubit system that we're testing and a 4x4 qubit system that we're testing. And so we'll probably have more to say next year, maybe even in this forum, about how that's going.
Otherwise, we'll have a talk from your group every month.
That's good. We're on it. So what I would say is that those are real questions that we need to answer, right? But it definitely eliminates one form of crosstalk that right out of the box is important, which is that, I know that I have a qubit and it's got a neighbor, say north, south, east, and west. I'm trying to calibrate north, but east, west, and south keep talking to me, and I wish they would just be quiet, right? So it's a way to eliminate that. Now, that's not the only crosstalk we'll have in our system, right? Of course.
Yeah.
Now, the linearity question is very interesting. And so we are working with Qiskit, in fact, on an interesting question related to this, which is, how do you handle calibration if the calibration may be locally linear in phase space, but globally is nonlinear? And Qiskit has done a lot of work in what they call X parameters, which are an extension of S parameters. And so they've thought a lot about how you would calibrate nonlinear systems in general. And I'm hoping that some of that mathematics that they've worked through can be applied here.
Well, that will be actually really great to know. I would love to see that. I should take a few more questions here. So there's a question from the audience. Thank you very much for the great talk. General question: what type of power spectral noise density do superconducting qubits usually see? Yeah, well, we certainly see 1/f spectra, especially if you have a squid loop. A tunable qubit is susceptible to flux noise, and flux noise, magnetic field flux noise, is generally 1/f distributed. Now, if you're sensitive to charge noise, that can also be 1/f type distributed, depending on the frequency. Now, if you get to high enough frequencies, right, then of course you can start to be limited by basically spontaneous emission effect. Well, not spontaneous, driven, stimulated emission effect due to these classical noise sources out at the qubit frequencies. So then, it can be both. But basically 1/f noise is a very common form of noise. Now, having said that, 1/f noise is often constructed from a number of two-level fluctuators, right? And if that number is very large, then it looks basically 1/f-like. But we've measured using these noise spectroscopy protocols in the past cases where you can actually see directly what looks like a Lorentzian type feature on the back of 1/f noise. So you have basically 1/f, but sometimes you see a little feature, and that's presumably due to a strongly coupled two-level fluctuator
that's modifying this otherwise sort of ideal 1 over f background. And what's interesting is if you go to that point, you can actually see, if you want to look at that, that's in frequency space. If you want to look at that in time, you can do a Ramsey or a spin echo experiment, and at a time that corresponds to that frequency, you'll see structure also in the decay functions in time. And so we've published those results, I think around 2014 or 2015, if you'd like to take a look. But you can see it. And so the 1 over f spectrum is sort of an idealization in the limit of many weakly coupled fluctuators.
Thank you, Will. And I think this is a quick one because I know you have a paper exactly on this question, which is how are the phasing times different for different levels, like between 0, 1, 2, 3, and so on?
Yeah, that's right. So the dephasing times, they're one thing, and they depend on the noise source. In fact, in particular, as we saw it, right, flux noise tends to be the same for every level transition, at least at the lower levels, and then but say photon shot noise would be different in a predictable way. What we have seen is that the T1 will decrease as you go higher into the manifold, and one intuition for that is basically that you have more levels that you can decay into. So if you're at, say, you're looking at the transition level 4 to 5, or don't even think of it as a transition. I'm in the 5th excited state. How long will I stay there? Well, of course, you can relax to different transitions below you, and so it makes sense that the lifetimes higher in the qubit are going to be generally speaking, less than lower in the qubit, particularly for these weakly anharmonic, qubits, which are basically, look like a lot like harmonic oscillators.
Yeah, I guess my intuition, and maybe this is wrong, was that if I have 4 photons in the resonator, I now have basically 4 times the chance to have one of them decay into the same noise bath. I mean, it's a little more complicated because it's actually correlated decay because they're all coupled to the same bath. But naively. And I think I remember from that paper you showed that T1 had a very nice linear, at least for transmodes. I don't think there were flux tunable in that paper. It was just a very linear, nice curve that was exactly slope 1 or T1 and decay.
Yeah, that could be. I'd have to go back and look. I think it was around 2013 or so. Yeah, I would have to look. But we did do that analysis, and yeah, it definitely decreased, right? The T1 went down as you went higher into the manifold.
There are many more questions, but unfortunately, I think we have to kind of wrap up here. So I will invite you folks to save those for next time we have Will or someone from Will's group on the seminar. This is becoming the running joke now that we have so many talks from Will. So thank you very much, Will, for taking this one yourself.
Yeah. Thank you, Zlatko, and really appreciate the invitation. And thanks to everyone for listening in. I'm glad to have you.
Yeah, I think you can see in the comments there were many, many very positive thank you and great talk, and I'll let you read those afterwards. But I'd like to, with that, thank you, folks, for tuning in to the Qiskit Live seminar series. I'd like to thank you, Will, for, again, taking the invitation, for the great talk and answering the many, many questions. We're 20-something minutes over. And this is the final talk of this year, but we'll be back in January, Friday at noon Eastern time, and we'll continue with after the holidays. So you can go back and watch this talk by Will. It will stay live. And I think with that, happy holidays. Thank you, everyone, for tuning in. Thank you, Will, for the great talk, and we'll see you next year.